right, so I am online, waiting for the class to start in about 4 or 5 minutes. If you guys have any questions, now is a good time to ask because we are right before the start time of this class.
I do have one question. This is
Yeah,
somewhat unrelated. Um, is there any way we could get access to the power server? I mean, well, yeah. I was gonna ask this when we were actually going to class because it was nice to have a server that we could swap to different computers. But now since I'm home all the time, I guess it doesn't really matter. Is
okay.
anyways, would we be able to get access to it if we asked? Possibly
Depends on for what purpose are you talking about, for the class,
programming.
for
Yeah, for
programming?
programming. Yeah.
Mm, and specifically, what programming language are you
C++.
targeting? C++?
C or C or C++.
I think the best way to do it is to get code blocks. Would that work in your application?
Oh, no. I would use it. The reason why I'd ask is because it was nice to have to be able to go like swap to different. Like I have like several computers. I have a laptop, desktop, and whatnot. It
I
was nice
see.
to swap
Okay.
between them.
There's
Or
a
would you would
there's a better resource actually. I think okay, what is the name of that place? It's an online place where you can have a Replit. That's it.
okay,
Replit.
Replit?
Yeah.
I'll try that out. It was just that's the only reason. I mean the compiler was nice somewhat,
Yeah,
but
so Replit is actually even better because first of all you don't need a command line like SSH or anything like that to access Replit. You can do it using a Chromebook because it's all web based,
nice.
and
Okay.
yeah, and also you can get a free account on Replit too. The free account doesn't do as much, but for most basic programming, if you go to the pricing tag, the starter, which is free, you can have up to two multiplayers, so you can actually work with somebody else. I guess that's what it means. 100 megabytes of storage. If you have a megabyte of source code for any one of your homework assignment, I would be super impressed. Because source code
Yeah.
doesn't take much space. Half a gig of RAM, point 0.5 to point 0.2 to point 0.5 virtual CPU. That's a lot for the typical homework assignment that we do. So the hacker one, is not too expensive. I don't think most people would even need it, unless you want multiplayer. This one has unlimited multiplayer, so that means I'm guessing other people can interact with your program, but I'm not. Uh, I don't use Replit myself too much, but I have seen people using it for all kinds of programming assignments and also learning a new programming language. Does anyone else want to kind of comment on this? Because I don't use it myself.
Yeah, I've heard of it once, like from my 300 professor, but we never actually used it. The only thing I'm used to is mostly code blocks and GitHub. And I was gonna use GitHub, but that's a little bit different. That's more of like a sharing site where you actually share your code. So,
GitHub is for what we call revision control, and I think Replit actually can work with GitHub too. So if you look up
oh
GitHub
really?
and Replit, um, yeah, you will find that they can work together.
All right,
Yeah,
all right. Thank you. I really appreciate it.
yeah, they can work in conjunction with each other. Let's see. I'm just trying to find. Yeah, pretty sure you guys would be able to find that. Yeah, so you can post any repository to import. So you can basically import a
Oh,
repository
GitHub.
from
All right.
GitHub onto your Replit account. But in that case, you might have a lot more your source code because your project is probably a bigger project in that case. Um, but it doesn't mean that it has to be that big. I mean, it can still be a fairly small project that you can do it without paying for Replit.
Yeah. All right. Thank you. It was kind of a pain to have to switch over because I'd usually program on desktop, but at
Mm-hmm.
college I program on my laptop. So
Ah,
thank
okay.
you.
Yep, sure. Yeah, I use Replit to play with Prolog and some other obscure programming languages. I mean, it has a lot of kind of funky languages on it. All right, so I guess it is time to get started with the class. So we are continuing with the practice exams, and this one is on the shared drive already. And let me just kind of go back and so I can point out which one I'm using right now. So this is the one that is 2019 spring semester. So when you go to the shared drive, let me go back to the shared drive. Actually, this is in the shared drive. Okay, I'll just go ahead and show you which one. So it's this particular one that I'm looking at right now. It's 1193 dash x1 dash 00.pdf. So if you want to follow along, you can go ahead and open the PDF yourselves, or you can just kind of watch the video as I go. Okay, so it's up to you. All right, so question one is something that we talked about already. It has to do with functions and set operations in general, so that's not going to be in our test. Question two has to do with the folding problem, so that's not going to be in our exam two. Remember, this is exam one from a previous semester. Question three of six, we just talked about it the other day, so that one is pretty much done already. So what we'll do now is to start with question number four. Question number four also talks about um, relations. So we have symmetric and anti-symmetric, because those two, even though the name is very similar and one seems to be the opposite of the other one, they're not exactly that. So what we want to do is to look at the combinations of, if we defined a set X to only have two elements, which is 2 and 11, we want to find out, can we create a relation for all four of these combinations, and if not, why is that the case? So I just want an English explanation, not necessarily a mathematical proof to do that. Okay, so let's go ahead and try to figure out the first one. Okay, R is both symmetric and anti-symmetric. Okay, and you can only have, and the relation is defined over 211 as a set. All right, so let me go bring up my mouse pad here so we can actually work on this one. All right, so we'll start with something really simple. Okay, we'll just say, what if R is empty? If R is empty, is it symmetric? Does anyone want to comment on that?
Yes, it is symmetric.
Yep, it is automatically symmetric. And what about anti-symmetric? So you might want to dig up the definition first if you're not sure. But is an empty relation automatically anti-symmetric? Or better yet, what does anti-symmetric mean in the context of relations? No one remembers what is anti-symmetric? Okay, so anti-symmetric is basically saying, for every pair of elements from X, okay, for every EF in X. So you can pick EF to be the same thing, you can pick E and F to be different, okay. So for every way to select two elements, okay, not necessarily unique in X, the following has to be true, okay. So it basically says ERF and FRE implies that F and E have to be the same, or E equals F. Okay, so this is the definition of anti-symmetric. So every time you see an implication, that means if you can make the left-hand side of the implication false all the time, then the implication is going to be true all the time. Okay? All right, so in this case, if R is empty, then ERF and FRE are definitely going to be false, because no element in the set relates to any other element. So that means when R is empty, it is R as a relation is also going to be anti-symmetric. Is that okay? Does everybody understand this, or are there any questions? So the answer to the first bullet point here, R is symmetric and anti-symmetric, is easy. R is the empty set. Okay, or at least this is one of the ways where um, we can define R. Do we have any questions about the first bullet point?
No, I don't think so.
Okay, all right. So let's move on to the second bullet point. The second bullet point wants R to be symmetric, but it is not anti-symmetric. Okay, so we're going to move on to the second one. So I'm just restating the problem over here, so this way, if I need to, I can move this one up. So in this case, we know R is not empty because we have used that one already. So now we have to construct an R. So we have to put something in between the braces, if possible, so that R is symmetric, but it is not anti-symmetric. So the question is, how do we make something does not fulfill a particular, it doesn't have a particular property? In this case, it is not anti-symmetric. So excuse me, for something to be not anti-symmetric, all we need to do is to find a particular E and a particular F so that ERF and FRE is true, but E equals to F is false. That's basically what we need to do. So but we still want it to be symmetric, okay? We still want it to be symmetric. So one way to do this in the question that I can only use 2 and 11, okay? So if I have 2, 11, which means 2 relates to 11, and then I also have 11, 2, which means 11 relates to 2, that will satisfy this particular requirement because it is symmetric, okay? And it might be helpful to revisit what does it mean when I say a relation is symmetric. So in the case of symmetry, it basically says for every EF in X. So once again, E and F can be the same, they can be different. I just have to pair each possible E with every possible F. Okay, the following has to be true. So in this case, all it's saying is ERF if and only if FRE. In other words, if I can find that E relates to F, then F also has to relate to E. But if one is missing, the other one should be missing as well. Okay, so this will satisfy the requirement of being symmetric because 2 relates to 11, 11 relates to 2, and 2 does not relate to 2. But that's okay because we can have that missing in on one side and it has to be missing on the other side, and then 11 also does not relate to 11, which is fine as well. But this is not anti-symmetric. Why is it not anti-symmetric? Because if I pick E to be 2 and I pick F to be 11, then we have these two being true, so the conjunction is true, but then at the same time 2 does not equal to 11, so the equality is false. So now we have true implies false, which means the implication itself is false. If I can find one instance of E and F so that this requirement is not satisfied, then the universal quantifier itself, which is the for all, is going to be false. So this is the answer to the second bullet point. Do we have any questions about the second bullet point in the question? Let me show you the second bullet point here. All right, so I'm assuming there are no questions about this one. Let's move on to the next one. So the next one is, what if we want it to be not symmetric, but it is anti-symmetric? Okay, so we'll copy and paste here. It is not symmetric, but it is anti-symmetric. Okay, so is it possible? So what does symmetry mean? Okay, we already quoted what symmetry means. So in order for a particular relation not to be symmetric, we have to be able to find one and not the other one. Okay, so we can now start to construct R so that it has one of them, like 211, but it doesn't have the other one or the 11 too. So this will definitely meet the requirement of not being symmetric. The question is, it is not symmetric, but is it anti-symmetric? Well, we look at the anti-symmetric definition. The anti-symmetric definition requires both ERF and FRE to be true in order for the second part to be evaluated. In other words, if one of these two is missing, if E only relates to F but F does not relate to E, then it is automatically true. At least the implication itself is automatically true. So when we look at this particular R, it is anti-symmetric, but it is not symmetric. Do we have any questions about this one? This answers the third bullet point of the question. No questions?
I just got to be careful about that implies in the anti-Semitic
Oh
definition.
yeah.
Oh yeah, that seems key here.
Oh yeah, the implication is a big one, particularly because we don't really use it as an operator in regular programming, so it is a kind of more of a novel operator from our perspective. But it really is just a Boolean operator like and or, except it's the truth table is kind of funky compared to the other ones. So are we good with the third bullet point? Shall we move on to the last bullet point?
Is Krishna's assumption correct? Krishna posted
In the
a
chat.
question
sorry,
in the
I did
chat.
not
Is
say.
her assumption correct as well?
Yes, that is true as well. So if you only have 11.2, that is also meeting all the requirements of not being symmetric, and it is anti-symmetric. That is correct. Yes. So Krishna got it. All right, cool. You're welcome. I forgot to look at the text channel. Thank you for reminding me to take a look at the chat channel. I mean text channel. All right, so we are moving on to the last one. R is not symmetric and it is not anti-symmetric. So we'll go ahead and explore that one. So we don't want it. We want it to be not symmetric. We also want it to be not anti-symmetric. Okay. So we have already looked at a few things, okay? So we can now exclude the empty relation. We can now exclude the relation that has these two items. We can also exclude the relation that has this particular item here. So the question is, how many more relations can we consider? Well, there turns out to be there are still quite a few, but let's not try to do the exhaustive search. Let's try to look at the definition of symmetry and anti-symmetry and see if we can reason out, whether this is possible or not. And if it is not possible, we want to figure out why it is not possible. So we want it to be not symmetric. Okay, not symmetric means you can have one but not the other. So that means we have to have either 211 or 11.2 in it in order for this to be not symmetric, and the other one has to be missing in order for this to be not symmetric. But we also want this to be not anti-symmetric. In other words, we want these two conditions to be true and yet E and F to be different. That is no longer possible because we know that if we have 211 in here, 11.2 cannot be in here, because if 11.2 is also in here, then it is going to be symmetric. But since 11.2 cannot be in here, we cannot make it anti-symmetric, because in order for something to be not anti-symmetric, we first need to make sure that this conjunction is true. But if 11.2 as a 2 tuple is not in R, then the highlighted conjunction has to be false. And if that is false, it doesn't really matter E equals to F or not, because that's just not going to work. So we can now say this is not possible. Okay, so we can say this is not possible, because in order for R not to be symmetric, 2, 1 of 2, 11 or 11, 2 needs to be in R, and then the other one not in R. But that means the anti-symmetry. Okay, I'm going to move this up a little bit because we don't need to read the question here anyway. Because that means the anti-symmetric implication is going to be true because the conjunction is false. So that's enough explanation already, as far as what I need for grading purposes, because it basically states that if you make it not symmetric, then it can no longer, the requirement of not being symmetric makes it impossible to be also not anti-symmetric. So do we have any questions about this? Okay, Krishna is typing. Okay, I'll wait a little bit. Oh, okay. So maybe she's. So if one person is typing and direct messaging to somebody else, do I still see it as typing in this particular text channel?
You should no. It should only show when somebody has their cursor in the text box.
Okay. All right. Cool. All right. So do we have any questions about this? The answer to the question?
No, I think that was a pretty good explanation. Thank you.
All right. You're welcome. Yeah, Krishna is still typing, so I'm waiting a little bit and see. Okay, there we go. Is there a possible X where R can be not anti-symmetric and not symmetric? So without the restriction of we can only have 2 and 11 in X. So let's take a look at that one. Okay, so without the restriction, can we construct a R that is not symmetric and not anti-symmetric? And let me turn on, well, I can either turn on wrapping. Let's do that. Turn on word wrap. There we go. Alright, so without the restriction of what can be in X, can we define an R over X that is not symmetric and not anti-symmetric? Okay, let me think. Okay, so we'll introduce. So the way I approach this problem is, we know that with only 2 elements in X, we cannot do this. So we'll just go ahead and introduce one more element in X. So we'll look at X as 1, 2, and 3. And then we look at R and say, okay, what can we do with R so that it is not symmetric? So the answer is yes, we can definitely do it. Because we can have 1, 2, but 2, 1 is missing. Then we can have 2, 3, and 3, 2 in here. Okay, so I claim that this relation is not symmetric, and yet it is also not anti-symmetric. So we'll see why that is the case. Okay, this is not symmetric because 1, 2 is in R, but 2, 1 is not in R. Okay, so is that explanation good enough to as to why this particular relation is not symmetric? Okay,
Yeah.
very good. So now we want to show why it is also not anti-symmetric. So it is not anti-symmetric because 2, 3 is in R. Okay, and let me put things in parentheses so that they nest correctly. And 3, 2 is also in R. Okay, so this conjunction, which is the conjunction that we saw earlier, the conjunction to the left-hand side of the implication is true. Okay. But the implication wants 2 and 3 to be the same, but now this entire implication is false. Let me kind of go back to look at the I'll just go ahead and copy and paste this so that this way I can focus on both. Oops, that's not what I wanted to do. Copy, not cut. There we go. Okay, so I'm going to paste it over here just so that we can have a local reference to what is anti-symmetric. So do you see how if I choose E to be 2, F to be 3, then I make the conjunction true, but the right hand side of the implication is false. So that is why this particular R is not anti-symmetric. So are we good with this example? All right, very good.
Works for me.
All right, cool. So the fact that it is not possible, as a part of this answer to this question, has to do with X only having 2 elements. That's basically the bottom line. The restriction of the set itself is the problem, or part of the problem. All right. So we are now done with question number 4. Let's move on to question number 5. Question number 5 says, assume that X has 3 elements, 4, 20, and 23. Define a minimal relation R over X for each of the following cases. The first one is R is partially ordered, and the last one is R is totally ordered. Okay, so this question, implicitly asks, do you know what is partially ordered? Okay, so we'll go ahead and work on this one. So we know X has 3 particular elements, and those are 4, 20, and 23. Okay. So we want to define R so that R is partially ordered. Okay. So in this question, the first part is basically saying it is partially ordered but not totally ordered. The way I asked the question, because it's already asked, so that means you can use one single answer to answer both questions, because if you can find R so that it is totally ordered, it is also going to be partially ordered. You can have that one single answer. So I should have been more clear that the first one is asking about the R that is only partially ordered but not totally ordered, and then the second one is just totally ordered. Okay. But since I did not put that in, that means you can use one single answer to answer both points, because anything that is totally ordered is also automatically partially ordered. All right. So can someone remind me what is partially ordered? What properties in a relation do we need in order for R to be partially ordered? There are like 3 of them, I think.
It needs to be transitive, reflexive, and anti-symmetric.
Okay, it needs to be transitive, anti-symmetric, and transitive. Okay. So, as lazy as I usually am, we'll consider the empty set. Is it transitive?
Got to put in
I forgot about
reflexive.
the last one. Reflexive. Okay, there we go. Okay, so we'll still look at the empty set first, okay? So the empty set is transitive. It is also anti-symmetric, because we showed a little bit earlier why it is anti-symmetric. But it is not reflexive. Okay, so we cannot do it this way. So now we just have to introduce reflexively the reflexive part. So we have to introduce 4, 4, 20, 20, and 23, 23. Aha! Now is it still transitive? Do we remember what is transitive? Okay, so let's take a look at transitive. Okay, transitive means for every, this time we have to consider 3 elements, E, F, G, in the set X, the following has to be true. Okay, what has to be true? This time it also has implication. Okay, so now we have to look at the left hand side of the implication and go like, okay, what has to be on the left hand side? It is ERF and FRG on the left hand side, and then this part is ERG. Okay, so it has an implication, which means the only time the implication is false, can be false, is the left hand side is true but the right hand side is false. Okay, so now we look at the left hand side and we ask, how can you make this false? Excuse me, how can you make this true when these are the only two tuples in the set? Okay, and the answer is, well, they all have to be the same. E, F, and G, they all have to be the same in order for ERF and FRG to be true. Is that okay? Does everybody understand what I just said? Given the R that we have, the only way to make the highlighted conjunction true is E, F, G, they all have to be the same. Are we getting that? All right.
I think so.
All right. Okay, that's good. So if E, F, G are all the same and ERF is already in the relation, doesn't that tell you that ERG is also in the relation? Because they're all the same. E, F, G are all 4, 20, or 23.
Yeah, so you mean we're defining E as 4, F as 4, and G as 4, for example?
Yes, because that's the only way to make the conjunction true.
Yeah, it makes sense to me.
All right, cool. All right. Excuse me for a little bit here. My cat just kind of climbed its way on my shoulder. All right, so that means it is transitive. This particular relation R is transitive already. The next question is it anti-symmetric? So we want to go back and look at what is anti-symmetric, which is still here. So we have to say for every EF in X, if we find that ERF and FRE, does that imply E and F are the same? In other words, the only time this whole thing can be false is ERF and FRE are true, and then E and F are actually different. Okay? So now we have to focus on, okay, let's focus on getting this true first, because if we cannot get this true, then forget about it, okay? Because, by default, anti-symmetry has to be true. So we have to make sure that this is true first, and then we worry about, can we make this false? So now the question is, how can we make this true when R is defined like the way we have here? It's very similar to the other question. It's very similar to the analysis of the transitive part, because the only time you can have both ERF and FRE to be true is when E and F are the same. So they can both be 4, they can both be 20, they can both be 23. Is that working? All right.
Yeah, that makes sense.
But if that is the case, then E and F are automatically the same as well, because E and F are the same in order to meet this requirement. In this particular relation, that is the only way to meet the requirement of ERF and FRE. So that means we are also satisfying the anti-symmetric requirement. The only one left is obvious. Okay, is whether it is reflexive or not. The only reason why I introduced these 3 elements into R is to make it reflexive. So it is also reflexive. So this is the smallest set to make it partially ordered. Is that okay? And I have to make a self-correction too, because I did not read my own question carefully. So let me point out why I said I did not read my own question carefully. Because I did not read this part here. Define a minimal relation R over X. So minimal relation means you cannot remove any element from the set. If you remove anything, it's going to make it not meet the requirement anymore. So in that case, the answers to the 2 bullet points are not going to be the same. Are we still good so far?
So they would be individual answers, or this answer just wouldn't be, you couldn't answer this question with a single R.
your second statement is true. You cannot answer this question with a single R anymore. Because the minimal relation to answer the first bullet point is this one over here. But this particular relation is not totally ordered. Why is it not totally ordered? What is that one extra thing that we need in order for something to be totally ordered? Totally ordered means it is partially. Yeah, go ahead.
Is it E relates to F or F relates to E? And partially ordered.
Everything has to relate to something else. Everything has to relate to everything, one way or another. So if you choose any two elements in X, okay, one element has to relate to the other one. The direction does not matter, okay, but it has to relate. So that means 4 and 20, they have to relate. Now whether it's 4R20 or 20R4, well, that's yet to be determined. 20 and 23, they also have to relate. Now the direction, once again, can go in either direction, but it has to be at least one of the two directions. Is that okay? And the 4 and 23, they also have to relate. And that's totally missing in the R that we are looking at right now. Is that okay? Does everybody understand why this R, this particular R here, is not totally ordered?
So we would need
I get that
we
part.
would need to also have like 420, 423, and then 2023.
Yes. So we'll need those 3 additional elements in R in order to make it meet the other requirement of being totally ordered. That one extra requirement.
So, but we don't. Okay, so we only need 4, 20, not 20, 4.
That is correct. We only need one. Okay, so it's up to you to define which one you want to use, but you have to choose carefully. Okay, so to answer the second bullet point, let's go ahead and start with what we have here. It's still, this stuff still needs to be here because it still needs to be reflexive. So now you can choose and say, how do you want 4 and 20 to relate? Now, just for whatever purpose, we can say 20 relates to 4. Okay, so but this also sets the but then we also have to relate 20 and 23. So how do you want to relate 20 and 23?
Just like that, 20, 23.
Okay, so let's try this. Okay, now 4 and 23, they also have to relate. So how do you want 4 and 23 to relate? Do you want 423 or do you want 23-4?
423.
You want 423. Okay, so now we have to look at this and ask, is this meeting all the requirements? Because even though the smaller r is meeting all the requirements of being transitive and anti-symmetric, reflexive is okay. Reflexive, we still have this part as a subset of the new R. So the new R is definitely still reflexive. That's not our concern. The concern is it still transitive? Is it still anti-symmetric? So let's look at transitive first. Okay, by introducing these 3, are we still having is R still being transitive? And the answer is it is not transitive anymore. Okay, it's not transitive anymore because 4 relates to 23. Okay, so let me think about this. There's a reason why it's not. So we have 24, 423, 20, 23. Okay, so that part is okay. Alright, so in order for something to be transitive, we have to look at every way to choose 3 elements in X, and we want this to be true all the time. So that means the most restrictive part is the bridge element. F is the breach element. So in this case, there's only one breach element because it is the second item of a tuple and it's the first item of another tuple. That is our 4. So 4 is the only breach element. Does everybody see what I'm saying?
Yeah, I see it.
Okay, so 4 is the only one that can meet the role of F in this relation. So now we can say, okay, if F is 4, then what is E? E has to be 20, and then G has to be 23. And now the question is, does 20 relate to 23? And the answer is yes. So this actually does meet all the requirements. It is transitive. So let's check out anti-symmetric. So in order for something to be anti-symmetric, this has to be if this is never true, then we are good. If this is true, then we also have to make sure that this is true. So the first thing is to check ERF and FRE and see whether that can be made true. So when you look at this, not counting the reflexive part, this part here, the highlighted conjunction, cannot be made true by these 3 additional elements that we just introduced, because it's not these 3. If you just look at these 3 items here, it is not symmetric, and if symmetry is missing, then this portion cannot be made true for sure. So if this portion is never made true, then the implication is always true. So that means this relation is also anti-symmetric. So we are still meeting the requirement of being transitive, we're still meeting the requirement of being anti-symmetric, and we're still meeting the requirement of being reflexive. And in addition to these 3 properties, we also meet the requirement that every element is relating to every element in the set. So you can see how 4 relates to itself, 4 somehow relates to 20, or I should say 20 relates to 4, but it can be one or the other. And then 4 and 23 also relate. When you look at 20, 20 relates to itself, 20 relates to 4, 20 relates to 23. When you look at 23, it relates to itself. 20 itself relates to 23, and then 4 and 23 are also related. So that means we also satisfy that one last requirement in order for this to be totally ordered. So we can now say this is the minimum partially ordered relation, and this one is the minimum totally ordered relation. So do we have any questions about the answer to this particular question?
So going back to transitive, because in the definition it's so we're basically just looking for any case where we can set E, F, and G to satisfy all of that. We don't need it. We don't need all of the E's, F's, and G's to satisfy that.
No, okay. So one way to look at the transitive thing. Okay, so let me see if I can relate this. Okay, so let's do this in a loop. Okay, I'm not gonna make a function out of this. So I'll just say the result is by definition is by default true. So this is pseudo C code, and then we say for each E in X. Okay, do the following. So this is and for each for the outermost loop. So does everybody understand what I mean by for each E in X? This is a loop, and all it does is to use an iterator to go through every single element in X. Are we good so far? It's just a control structure that goes through every single element in X in each iteration. Are we good?
I guess so.
Okay. And then we set up a nested loop here, and it's almost the same. This time it is F. And then we set up yet another loop here, which is for each G in X. and for each. So now, when you look at this entire control structure, it's basically, by the time we get into this portion here, by the time we get to the blinky cursor at this point, that will basically experience every single way you can choose 3 elements from X. Are we okay so far? Yes? No? Maybe? Are we good?
Works for me.
Oh, okay. Go ahead. I didn't hear from all of you. So, one at a time. Are we good? Maybe?
Yes.
We're good. Okay. So what we're going to do to result is going to be ended with itself, and then the other part is just this stuff here. Okay, so I can actually just copy it down here. Copy and paste. So this mathematical expression can be implemented using this particular control structure. Is that okay?
Yep.
Okay. So the tedious way to evaluate, whether this whole thing is transitive or not, is really just to come up with every single way we can choose, 3 elements out of the entire set. Okay. So that means we have to consider, if I look at EFG as a 3 tuple, okay. So E equals to 4, F equals to 4, G equals to 4. We represent one case for this statement to evaluate its assignment. Another one, the next one is going to be E is 4, F is 4, G is the next element because the G loop is the innermost, and the 20, sorry, there we go. And then the next one is going to be E is 4, F is 4, G is 23. And then that will basically finish the innermost for each G loop. So we go back up to the for each F loop. So F changes and then G resets back to 4. So now we have E is 4, F is 20, G is 4 again. Do you see what I'm trying to express here? These are the combinations of what E, F, and G can have as we go through all the iterations of this control structure. Is
Right,
that okay?
and some of those, and some of those are not transitive, right?
No, they're all transitive. That's what I'm claiming. They're all transitive. In other words, when you look at this expression here, it is always true. It's always true because of the implication. Is that okay? There are only 4 ways of choosing E and F to make this part here true. Okay, because if you want to make the implication false, there's only one way to make an implication false. To make an implication false, the left hand side has to be true, and then the right hand side has to be false. Is that okay?
Yep, that's what I forgot. Yep.
Okay, so in order to make it false, then the first thing we have to do is to make the left hand side true. Is that okay?
Yeah.
Because if you cannot make the left hand side of an implication true, forget it. Forget about it. The implication itself is going to be true. So in order to make the left hand side of the implication true, in this case, there are only 4 possible cases to make this true. Okay, so I'm going to enumerate all 4 cases. So you can have E is 4, EF is 4, G is 4. That will make this requirement. That will meet this requirement. Does that make sense? Because
Yes.
okay, the next one, the other 2 are fairly, trivial because we basically just make E, F, and G being the same. Okay, we explored that a little bit earlier. Okay, so these 3 combinations of choosing E, F, and G will meet the left-hand side requirement, but also it's going to meet the right-hand side requirement because guess what? E and G really are the same thing. Is that good?
Yep.
Okay, but there's a fourth way. Okay, there's one fourth way to do it. Okay, there's only one extra way that this can happen, which is using 20 as E, 4 as our F, and then 23 as our G. That is the only other way, not using the reflexive elements, to make the left-hand side of the implication true. Because after all, 24 is here, and then 423 is also here. Is that okay? So now the question is, does E relate to G in this case? E is 20, G is 23, and 2023 is also in the relation. So even in the fourth way, this entire expression, the implication, is still true. Are we still good with this example, with the explanation?
Yeah, I'm still following.
Okay. So now the question is are there any other ways so that we can meet this requirement and not meet this requirement here? Because that's the only thing you can do to make this entire implication false. So the question is, can you find another breach value where it appears as the second element of a two tuple in one element of the relation R, but it appears as the first element of the other element of R. So we can search exhaustively. Okay, so we look at 4 and say, well, does 4 appear as the second thing? Yes. So 4 appears as the second thing here, but that's just the reflexive part, and we are already done talking about the reflexive part. The only other case is over here. 4 appears over here. So then the second question is, does 4 also appear as the first item in a two tuple? Yes. But this is the one case that we have already talked about, so we're good with that. The next question is, what about 20? Does 20 appear as the second item, not counting the reflexive item here? The answer is no. 20 never appears as the second item, so we know for sure that, if we choose F to be 20, then this conjunction is guaranteed to be false, which means this implication is guaranteed to be true. So 20 does not make this particular implication false. What about 23? Well, 23 does appear on the as the second item of a two tuple over here, so that's okay. But does it appear as the first item of a two tuple anywhere, not counting the reflexive part? The answer is no, it does not appear, over there. So we know that if we make F equal to 23, this particular condition is going to be false, unless there's only one case you can make it true, which is to consider this one as one of the two items in the conjunction. But that's that's going to be trivial. So are we okay with this analysis?
Yes, thank you.
All right. Okay, cool. So that answers the question 5 in this test. And now we are moving on to question number 6. And this one is about cardinality or aleph null. So we are not going to be having this question or this kind of question in the second exam because we got it in the first exam already. So are we okay so far? Is everybody feeling comfortable with relations, or more comfortable than before?
Definitely.
Okay, so we got half an hour left. Okay, and I think we spent about half an hour on past exams on Monday's lecture. So it's up to you guys. What do you want to do at this point? Do you want to go over even more examples, or do you want to kind of move on to a newer topic?
I would vote for more examples.
Yeah, I was going to say more examples.
Okay.
I agree.
All right, so we'll go ahead and take a look at more examples. So we'll go back one more semester, which is this is from 2018 fall. So the way I know this is from 2018 is the 1/8, and then the fall is indicated by 9 as a digit as opposed to 3 as a digit. 3 is for spring, 9 is for fall. And this way of encoding a semester is actually internal to the scheduling program of Los Rios. It's just that you guys will never see it because that's usually hidden from the section code of a class. So we'll take a look at this one. This is the second exam, but the scope of the second exam varies a little bit depending on what material I was able to go over by that time. So question 1 of 5 is saying you're given that the following represents everything known to be true. Okay, and first re-express psi as a CNF, and then consider phi 0, and then use resolution and proof by contradiction, show whether phi 0 is a theorem of psi or not, and then show all your steps. Do you guys want to do this, or do you, it's up to you. This one is basically the same nature as the homework assignment. You have to convert something into a CNF first, then you also have to convert the negated theorem into a CNF, concatenate those two CNFs, and then use resolution to see if you can get to a contradiction. So we got yes, okay, so we got 2 people saying, 3 people saying, okay, let's do it then. Alright, so I'm going to copy the question onto mousepad first. And in the exam, because this time when we do this exam, it's done online. So that means you guys will also be able to use at least a text editor. I'm not going to assume anything fancy, so I'll just assume that you guys can use mousepad, notepad, or something like that, and you can type directly into the exam document, which is going to be either a Google Doc or a Google Sheet. So that means we're going to use the shorthand that we have been using in this class, which is this is not P, this is not Q, and this is implying R. This one is 1189 exam 2.
Thank you.
Alright, so the first thing we need to do is to convert psi into a CNF. So this is psi. Alright, so we'll go ahead and convert this into a CNF. The first thing I usually do is to get rid of the implication. So we have to use the definition of implication to get rid of the implication. So I negate the left-hand side and then or the right-hand side. And now I can see that we have a negation of a disjunction. So we can use De Morgan's law. So De Morgan's law will give us not P, because we're distributing the negation into the components of this particular disjunction. So this component, not P, is negated itself. But we also have to remember that a disjunction is, when we negate a disjunction after applying De Morgan's law, the disjunction becomes a conjunction. So we have this. And to make sure that we understand that we have to perform the AND first, we do it like this. So this is the opposite of what we want, because we have a overall disjunction where each component of the disjunction is a conjunction. So this is DNF, or disjunctive normal form. So in order to convert this into, well, first let's simplify a little bit first. Okay, there we go. So now we look at this and go like, we just need one more step, because we can distribute the R using the usual distribution in normal algebra. Now we have a CNF. Do we have any questions about how psi got converted into a CNF at this point? Okay, so that answers this particular question of re-expressing psi as a CNF. So now we have to look at phi 0. Okay, so phi 0 is the proposed theorem, which means we have to negate it first in order to, and then convert it into a CNF. So we have to look at the negation of phi 0. which is now the negation of whatever phi 0 is defined to be. So it is Q implies P, the whole thing, or yeah, so we have to make sure that there's a big parenthesis around the whole thing. Not P and Q and R. Okay, there we go. Alright, so the negation is over a disjunction. In other words, or we can expand this first. Okay, we'll go ahead and expand the implication first. So the implication becomes the negated left hand side or the non-negated right hand side, and then we have the not of not P and Q and R. Okay, and then we look at this and go like, there are several directions we can take. The first one is we can dissolve the this parentheses here, this particular pair, because we have an or inside here, and then outside of the or is another or, so we can go ahead and dissolve that. So now we have not P or not Q or P, or not P and R and Q, like that. And then we can now apply De Morgan's law and distribute the outermost negation to every single component of the disjunction, but also at the same time turn the disjunctions into conjunctions. So now we have not Q and not P and the negation of not P and Q and R. Okay, do we have any questions up to this point? Alright. Then we do a little bit of simplification. Not Q is just Q. Not P is not P. And now we have to apply De Morgan's law again, because this negation is applied to the conjunction between not P, Q, R. So we can now say this is now becoming not P, or not Q, or not R, like that. So if I want a CNF, it is already a CNF, but I can simplify this just a little bit more. So we have P or not Q or not R over here. Are we still doing okay so far? This is the negated proposed theorem. Yes? Okay. So if we are good here, now we have to concatenate the two. Okay, so now we have to say what is psi and not phi 0. Okay, and because you're going to have access to Notepad or something that can do copy and paste, so this really should not be too big of a problem copying and pasting like that. Okay, so now the question is, what can we do to resolve between these terms? Can we resolve this whole thing to a contradiction in the end? Okay, so I personally would just kind of do it systematically. In other words, I look at the first one and then I ask what can it resolve with in order to give me some additional terms. So we can look at this P and then we look at this not P here and go like, those two can resolve. So if those can resolve, okay, we'll go ahead and copy this down here. And we just add a new term. After those two are resolved, we get a not R. We get a single R, sorry. We get a single R because the P cancels out with the not P, and then the rest of each disjunctive term is concatenated. This disjunctive term has a plus R or the or R. This disjunctive term doesn't have anything else, so we only got a single R left in here. Okay. If I want to do this systematically, I can look at this and look at this over here and say, well, those two can also resolve. Okay, so I look at this P and I look at, I look at the R and I look at this not R over here and say, well, those two can connect and resolve. So when that resolves, let's see what we end up with. So what we end up with here is the concatenation between those two. So one side has a P left, and then the other side also has a P, but we don't have to repeat that. and then the not q can be placed here. So are we still doing okay so far? I'm not doing any other type of derivation or simplification. I'm only using resolution here. No questions? All right. So at this point, I'm done with using the first disjunctive term. Now it's time to look at the second disjunctive term here, which has q or r. So we now say, what can it resolve with? So the first thing it can resolve with is to resolve with this particular r, not r over here, or this not q over here. So this is also a good place to explain that you cannot resolve two variables at the same time. You cannot say this one has got a non-negated q, a non-negated r, this one has got a negated q and also a negated r. Can we resolve both at the same time and only have p remaining? The answer is no, you cannot do that, because if you do the resolution one by one, you will find out that it will give you a different result of looking at both at the same time. So the answer is no, you cannot resolve both at the same time, but we can certainly do one at a time. Okay, so we can resolve q based on q first. So now what do we have left? So of the first term, of the first disjunctive term, we got the r left, and then with the second one we got p and not r left. Okay, so you look at this thing here. Okay, you go, that looks suspicious because we have r, not r in the same disjunction. That's just true. Okay, so we'll go ahead and leave it here, but it is not a very useful term, after the resolution. Okay, so we continue to look at q or r and say, can it resolve with anything else? Cannot resolve with r by itself, but it can resolve with this one here because we have p or not q. Okay, so we can say this q and this not q here can resolve. Okay, and the result of that resolution is to introduce r by itself. Let me see. No, it's r on one side and p on the other side, so it's p or r. But that's not a new term because we got that term already. I'm off from the screen. Oh, okay. Thank you. Not that window, but I moved the wrong window. This one over here. There we go. Okay. Okay, but you can see that this p or r was already here, so we did not introduce anything new. But I'm still gonna put it here, just so that we remember that that term is introduced. And then we have this r here that can resolve with this not r. So we'll go ahead and highlight that. So we look at this r, and then we look at this not r over here, and not very surprisingly, we also see p or r. In fact, this whole term is really useless. It's really just true. So it doesn't produce any new resolution terms. So now we can move on to this q. This q can resolve with this not q over here. Okay, it can also resolve with the other not q over here. Remember, I'm not doing any simplifications, because if I were to do any simplifications in a conjunction, the more general term, which is this term here, can be simplified out. Okay, but I'm not doing any simplification here. So, but I'm getting a little impatient, so I just want to get to the final answer as quickly as possible. This is the way to do it. Okay, because if this q resolves with that not q, it would give us a p as itself in the CNF. Okay, so we resolve this, and now we just have p left. Okay, so at this point, I think most of you can see that, oh, we don't need to do it the old way anymore. Just look at this not p, look at this p over here, and they certainly resolve to a false. Okay, which is represented by a 0 here. So now we have a contradiction, because the 0 or the false is one of the terms of a pretty long conjunction. Okay, this entire thing is a conjunction. But when you look at a whole conjunction and one of the components of the conjunction is false, then the entire conjunction is going to be false, which means psi and not phi 0 is false. So when you combine what is known to be true and the negated theorem, and it says that is going to be true, okay, then you can and because of this, now we can say phi 0 is a theorem. Because psi and not phi 0 is false. So that's the answer to the question that we are on. Do we have any questions? Go ahead. Oh.
On the test, does it
Yep.
matter if we write down the psi and phi parts?
It is important to identify what this is. So it is important to kind of write down psi and not phi, because one part, which is which part? Yeah, so one part of this is coming from what is known to be true, and the other part is coming from let's negate what we think that what is known to be true is going to imply, and see what happens. So it is important to write down this portion here, because otherwise I don't know what this whole thing is. Okay.
Okay, yeah.
Yep.
Hey,
And I got
Professor.
yeah.
Oh,
So
okay. So all the way up at the second equal sign, after we were able to get the R resolution, can't you simplify? So there's a Q and a not P in the conjunction, right? In the O.
okay, let me turn on line numbers, and I also have to go back to answer the questions in the text. So go ahead. Let me answer next question first. Which line are we referring to?
Okay, 79.
79. What about that?
Yeah. So there's a Q and a not P in the overall conjunction there, right?
There's a Q right here.
Yeah. And then the not P.
Yes.
And then there's a P or not Q or not R.
Yes.
I think, and I could be wrong, but I did this by truth table, but you can dissolve P and the not Q in that disjunction and leave just a not R.
Yes.
Because
Yep, you can do it that way too. Yep.
Okay, so that would be valid to
That would
simplify
be
it right
valid.
there.
Yeah,
Okay.
but I still want you to resolve one variable at a time. So you would use this Q to resolve with this not Q. Then you have P or not R left. Then you proceed to use this not P to also combine it with this P here. Then you have not R left. And then at that point, that not R can easily resolve with this particular not R here, and you can get your contradiction that way too. Yes. So the path that I have chosen is not the only way to show a contradiction. It is just one of many ways to get a contradiction.
Okay.
Yeah, but I still want you to do one when you perform resolution. I still want you to use one term at a time, and not to look at the negation of this conjunction is this disjunction here, because of De Morgan's law. You can kind of figure that out, but I don't want you to resolve two terms at the same time. I still want one term at a time. Okay, so I'm going back to the text channel, and Brenda asked, so once we hit 0, we know to stop and conclude it is a theorem. That is true, because once you have a 0, or once you have a false in a conjunction, the conjunction is now false. No matter what additional resolution you're going to do, the conjunction is false, because all it takes is one of the components of an and to be false, and then the entire and is false. So Brenda is correct about that. Kevin confirmed that. Good. And then Bo asked, since any x and false is always false, okay, so you can no longer make it true anymore. That is also true. Okay, so all of those are good confirmation that we are getting a handle on this kind of question. I give you what is known to be true. I give you a proposed theorem, or just a general statement, and you have to decide whether that statement is a theorem or not. When we use the word theorem in mathematical proof, all that is really saying is a statement is implied by what is known to be true. That makes it a theorem. All right, so let's go back to the exam, and I have to be mindful of our time. We got about 20 minutes left, so we move on to the second question. And this one we are not going to ask because we have not talked about the binomial theorem and stuff like that. And then this one I'm not going to ask, even though we have kind of introduced the omega thing, but counting and discrete probability is not in the scope of the second exam for this semester. This is question 4. It's using proof by contradiction. That is a interesting one because proof by contradiction is actually introduced up to this point. So let's go ahead and work on this one and see how we can prove this by contradiction. Be sure to show all steps proof by contradiction as well as algebra. Okay. Alright, so proof by contradiction requires the first thing you need to do with proof by contradiction is to identify what theorem are we talking about. So you have to look at the theorem. What is the theorem? So in the statement here, prove by contradiction that the following is true for all x in Z, blah 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 blah, and this is what we want to prove. Okay, this part here is the theorem. So we can now identify the theorem, and all it says, we can neglect to mention the quantifier, okay, which is the for all, and then we can say, if x times x or x squared is even, then x is even. Okay, this is the theorem. So now we have to negate the theorem. Okay, the negated theorem is, okay, so how do we express the negated theorem? Well, one thing that is going to be handy is not to look at this using the English sentence method anymore, but to use a more formal way, which is x times x is even, implies that x is even. Okay, so when we introduce the implication operator here, that makes it easier to express the negated theorem, because we can now just copy and paste this over here, and then we can apply a little bit of Boolean algebra, the one that we already know, which is to say this is not the case that not x times x is even or x is even. Okay, and can we move the window over? Yes, sorry about that. And there we go. Okay, so with this one, if we can now use De Morgan's law. De Morgan's law says not x times x is even and x is even. Okay, let me double check my. Oh, there's a negation over here because we're distributing the negation. Okay, so when we clean it up, okay, we just have x times x is even, but x is odd. Okay, all I did was to apply this negation to is even. If something is not even, it is odd. So are we still doing okay so far in terms of looking at what the negated theorem looks like? Are there any questions about how I got to the negated theorem, which is basically saying x times x is even and x is odd?
Where did the negation on the x is even come from?
Because we applied De Morgan's law, this negation, which is applied to the result of this disjunction, means that we can use De Morgan's law. So what De Morgan's law is going to do is to distribute this negation to both terms of the disjunction. So it will distribute it to this one, and as a result we end up with a double negation. But it will also distribute this negation over here to the other term of the disjunction, which is this one here, and as a result we end up with the negated x is even.
Yep, I got it. Thank you. I missed something there.
Okay, that's fine. Okay, so now we have the negated theorem, which basically spells out x times x is even, but x is odd. Okay, so we have x times x is even, but x is odd. Okay, so the question is, why is that false? Okay, is it possible? Why is it not possible? Does anyone want to prove that in algebra this is not possible?
2 times 2 is 4.
2 times 2 is 4, but how is that going to help us?
It's loud over here. I must have misheard.
Because
Okay.
2 is.
Okay, so if a number is odd, that means it is it's an even number plus. It can be re-expressed as an even number plus 1, right?
Right.
So we can basically find an n, so the x can be re-expressed as 2n plus 1. Okay, so I can say find n such that x is 2n plus 1. Are we good? Because
Yep.
x is odd, so we have to be able to find n as an integer, so the x can be re-expressed as 2n plus 1. So now when we look at x times x, it becomes 2n plus 1 times 2n plus 1. So 2n plus 1 times 2n plus 1 ends up as 4n squared plus 4n plus 1. Okay,
Plus 2.
plus 1.
2, not plus 1. Wait.
What?
No, wait.
Plus 1.
Never mind. I can't math today. Yeah, plus 1.
Okay, so now we can basically say that 4 times n plus 2 is going to be an even number. 4n is also going to be an even number plus 1, so that means this whole thing is going to be an odd number. Is that making any sense? If x is odd, x times x also has to be odd, which makes this not possible because x times x cannot be even. Are we making sense out of this one? Okay, let me just move this one more step. Okay, so I can re-express this as 2 times n squared plus 2n over here. All I did is to split the 4 into 2 times 2 plus 1, but every number that has a 2 blah blah plus 1 is an odd number. So this is basically saying x times x is an odd number, because we are now re-expressing x times x as 2 times some other number, let's say j, okay, plus 1, where j is 2 times n squared plus 2n. Is that okay? So j is going to be an integer, because this whole thing is an integer. So if I can re-express x times x as 2 times an integer plus 1, then x times x is odd, which contradicts with the claim that x is even. But that's the result of the negated theorem. So the negated theorem is going to end up with a contradiction, because x times x cannot be even and odd at the same time. Because here, okay, go back to. So this basically implies that x times x is odd. So now we can say x times x is even and x times x is odd as a conjunction is false, because x times x can be one of the two, but it cannot be both. So we have our contradiction, since the negated proposed theorem leads to a contradiction. The proposed theorem is in fact a theorem. So that concludes the proof. Are we doing okay so far? Are there any questions about the proof technique part, which is about proof by contradiction? Or are there any questions about the algebra part, which basically says how can we conclude that x times x is odd? There are no questions. All right, I'm looking at the time. It is 1:20 exactly. So I think we got through enough examples for this test. We are running out of time, Brenda. I can probably do more and then post it, over time, but as far as the lecture time is concerned, we are running out of time. All right, you're welcome. All right. So what I'll do is I'm going to end the lecture or the streaming, shortly. And then, as I develop the test for exam 2, I will share with you the format of the test. So I'll give you guys, kind of a sample of what it looks like. Probably using some, simplified, questions or questions that you have seen already. But I'll give you an idea of what I want the format to be in. And also what you need to do in order to take the exam. So those, extra communication will help prepare you for the exam in terms of knowing how to answer the questions, but it will not disclose the exact questions that I'll be asking. So are there any questions? And if I don't give you guys anything, send anything out, over the break, you can always just give me a ping and just kind of nudge me and ask, okay, do I have any examples of the format of the test, because I want you guys to know how to answer the test, how to use the tools and stuff like that, so that when we actually get to exam 2, all I'm really testing is your knowledge and whether you can problem solve, and not so much can you use Google Sheet or Google Doc. All right, sounds good. So I'm going to stop the streaming. Well, thank you. So I'm going to stop the streaming here. Oh, go ahead, Alexander. Oh, okay. Just thank you. Okay, very good. So thank you. I hope you guys have a nice spring break. I'm not sure what we're going to do with the spring break, because we still cannot go anywhere. Brenda is typing. Yep, stay safe. Make sure you get food. I don't think 6 feet away is enough, because the Mythbuster actually measured how far a sneeze droplet can go. And I strongly recommend people to watch Mythbusters, especially that one episode. Yeah, 6 meters, that's about it. I think it's 18 feet. A droplet from a sneeze can go 18 feet. Yep. Or you can put a cone around yourself, like use plexiglass to make a cone, make a huge, cylinder, and wherever you go, that cone of, not silence, but cone of virus-free zone goes with you. Bubble boy. Yes, sneezes does travel 100 miles per hour when it's exiting. Yes, so in gun speak, that's your muzzle velocity. Unfortunately, sneeze droplets, are very light, so they slow down very, very quickly over distance. Meters is just European feet. It's about 3 European feet. Funny. All right, so I'm gonna stop the streaming, and also the DVR, but I'll stay online for a little